Hello everyone. Today, my presentation will focus on section 6.2 of chapter 6, Memory Hardware Expansion. Specifically, we will look at how to expand bit width and bit capacity using hardware circuits. Before we dive into the expansion techniques, let's first review the hardware pins of a single memory IC. Please look at slide 8, which shows the pin configurations for standard EEPROM chips. Taking the 27C256 chip as an example, you can see the several critical pins. First, the address pins, such as A0 to A14, which are used to locate specific data. Second, the data pins, or output pins, labeled O0 to O7, which output the data. Finally, the control signals. The most important ones are chip enable and output enable. These are typically active low signals. Understanding these basic pins is essential because when a single chip's width or capacity is insufficient, we expand them to connecting these very pins in specific hardware or configurations. Now, let's move on to slide 9 and discuss the bit width expansion. Imagine our CPU has a 16-bit data bus, but our available memory chip, like 27C256, is organized as 32K by 8 bits. A single chip can only output 8 bits at a time. To solve this, we connect two chips in parallel. Please look at the address bus on the left. The 15A address bus A0 to A14 are connected to both EEPROM 0 and EEPROM 1 simultaneously. This means when the CPU sends an address, both chips are activated at the same time to access the same memory location internally. Next, look at the data bus on the right. This is where the width expansion happens. We wire EEPROM 0 to connect to D0 through D7, handling the low byte. Then, we wire EEPROM 1 to connect D8 through D15, handling the high byte. By doing this, we perfectly combine two 8-bit chips into a single 16-bit memory module. Additionally, their control signals, such as chip enable and output enable, are tied together to ensure they operate synchronously within the same clock cycle. Next, what if our width is sufficient, but we need a larger storage space? Let's turn to slide 10 for bit capacity expansion. Suppose we still use 32K by 8-bit chips, but our system requires a total contiguous address space of 64K. We cannot simply tie all the control lines together like we did before. If two chips output data to the same 8-bit data bus simultaneously, it will cause a data collision or a short circuit. Notice on the right side of the diagram, the data outputs D0 to D7 from both chips are connected to the exact same data bus. To prevent collisions, we must ensure that only one chip is enabled at any given time. How do we achieve this? We use the higher order address bus as you can see on the left. A0 to A14 are still connected to both chips to find the specific location within the 32K space. However, we use a high order address line. In this case, acting like A15, along with the decoder or inverter to control the chip's select signals. When the lower half of the address range is accessed, The hardware logic sends a CS0 signals to enable EPROM 0. When the upper half is SX, it sends a CS1 signals to enable EPROM 1. These address decoding techniques allows us to logically stack the two chips, creating a seamless larger memory space. Finally, let's look at the calculation example on slide 11. There are three different scenarios here to test our understanding. The first question asks how to form a 122K by 8-bit memory area using 2764 ICs. First, we must know the spec of a 2764 IC. It holds 64K bits. Dividing 64K bits by 8 given us 8K bytes, meaning its organization is 8K by 8 bits. Since the system's required data width is already 8 bytes, we only need to expand the capacity. 128K divided by 8K given us 16. Therefore, we simply need 16 pieces of these ICs. The next example asked how to build a 256K by 16-bit memory using 8K by 8-bit ICs. We can break this down into two dimensions. For the width, the system needs 16 bits, so we parallel two chips. For the capacity, 256K divided by 8K give us 32 banks. 32 banks multiplied by 2 chips per banks equals 64 pieces. The third example uses DRAM. To build a 512K by 16-bit memory using 256K by 1-bit DRAMs. We first look at the width. Since each chips only output 1 bit, we need 16 chips in parallel just to form the 16-bit data bus. Then, to reach the 512K capacity from 256K, we need 2 banks. So, 16 chips per bank multiplied by 2 banks give us exactly 32 pieces. In conclusion, memory expansion is a purely hardware-driven implementation. By precisely routing the address bus and data bus, and by cleverly utilizing chip select signals for decoding, we can use basic ICs to construct large memory systems that meet various specifications. That concludes my presentation. Thank you for listening.